Hi students, now we are going to derive the values of Cp, Cv and gamma for a linear triatomic molecule at normal temperature. Now the behavior of a linear triatomic molecule as well as a diatomic molecule will be the same at normal temperature. So the average kinetic energy per degree of freedom as usual it is half kT. And the number of degrees of freedom is equal to 5, similar to that of a diatomic molecule, isn't it? At normal temperature, both a diatomic as well as triatomic linear molecule will have the same number of degrees of freedom. So the average kinetic energy per molecule is 5 degrees of freedom multiplied by half kT. So it is 5 by 2 kT. Therefore, average kinetic energy for 1 mole, that is Avogadro number of molecules, that is epsilon equal to Avogadro number multiplied by, this is the average kinetic energy per molecule. So it is Na into 5 by 2 kT or 5 by 2 into NaK into T. The product of Na into K is equal to the universal gas constant capital R. Therefore, epsilon equal to 5 by 2 RT is the first step. If you differentiate this epsilon with respect to the temperature T, that will be equal to the specific heat capacity at constant volume, that is Cv, equal to du by dt, that is equal to d by dt of 5 by 2 RT. So here T is the variable, 5 by 2 R is the constant. So 5 by 2 R into d by dt of temperature T is 1 as usual. So what is the value of Cv equal to 5 by 2 times R? This is equation 2. Then from Mayer's relation as usual, Cp minus Cv equal to R or Cp equal to Cv plus R, that is equal to 5 by 2 R plus R. Taking LCM it is equal to 7 by 2 R. Therefore Cp equal to 7 by 2 R is the third equation. Then how to find the adiabatic exponent gamma, that is the ratio of Cp by Cv. So it is equal to 7 by 2 R divided by 5 by 2 R. Cancelling 2R on both sides, gamma equal to 7 by 5, that is equal to 1.40. So this is the final step. The adiabatic constant gamma for a triatomic molecule at normal temperature is gamma equal to 1.40, and this is the final equation number 4. I hope you must have understood well. Fine.